Hello everyone, we'll see more examples of DFA, Deterministic Finite Automata. See the first case. It says that sigma is A and B and we have some language L over sigma having only one string of length 1, that is the machine deterministic finite automata is expected to accept only this single string A. Start with some initial state Q0. Q0 on reading A will accept it, will go to the final state, say Q1. But still the design is not yet completed because I have to show the transition of B on Q0 and transition of A and B on Q1. Clearly, we do not want to accept any string that has B, so send it to the trap state. Say this Q2 is a trap state. Once we read A, single A, after that we do not want any of the symbols because we have a string of length 1 only. So therefore, if Q1 sees an A or a B, send it to the trap state. So this is the design for language L that has only one string of length 1 and the string is made up of symbol A. The next language L is having a string null. It accepts a null string. Null is accepted, so therefore the initial state is the final state. And we do not want to accept any other symbol other than null string. So therefore Q0 sees an A or B. It will go to the another state Q1. Q1 is the trap state. Okay, so the third case is that L is equal to 5. That is an empty language. An empty language is not accepting anything. There is no accepting state in this case. Either A or B keep on looping on this state, which is a non-accepting state, and the language is equal to 5. It is not accepting any string. Sorry, we'll see more examples. All string over A and B, including a null string, that is R is equal to A plus B whole clean closure. We need to accept this. So therefore, since it is accepting a null string, initial state is the final state. Any A or B is accepted by this. This is the DFA for the given regular expression or language. Any A or B, any combination of A and B are accepted, including a null. So we have only one circle, one memory element in this language. Strings of with length multiple of 2. String is we know sigma is A and B, that is we have any combination of A and B, and the string is of length 2. So the design of DFA would be read A or B, go to state Q1, read A or B, state Q2. Instead of taking Q2, what we will do, it says multiple of 2. Multiple of 2. So we'll make initial state as the final state. Null is also multiple of 2. So we'll read A or B, go to Q1, read on Q1 again read A or B, go to Q0. So this is something, the regular expression is of this kind, A or B square whole clean closure. So we can have a null string, we can have a string of length 1, length 2, minimum smallest is length 2, and then length 4 and so on. Just we can see by expanding this, if R is square raised to the power 0, we have A plus B square raised to the power 1, A plus B square raised to the power 2 union a plus b square raised to the power 3 and so on. So we'll see that we have all even length string including a null string. This will give us a null. This will give us all strings of length 2. This will give us all strings of length 4, all strings of length 6 and so on. And the machine would be like this. Q0 will accept a null, so it is final state. A or B will be on that is the length of string. Whenever odd, it will be on Q1. Whenever it is even, it will be on Q0. Let me take another example. There's a condition on strings, all strings of this kind, that is strings of A and B, and it ends with double A. If it ends with double A, we'll start with Q0. It is not a final state because null is not accepted. The smallest string I will have is double A. So read an A, go to another state, say Q1, again read an A, go to another state, say Q2 and accept it. Make an accepting state. Now the condition is that these two A has to be at the end of the string. After this double A, we can have any number of A that will have the last two symbols as a double A. So put this loop here. Any strings of having double A, the loop will have any number of A at the end, and we are accepting it. Now we'll complete this diagram. What will happen if Q0 accepts B? Any number of B, keep looping here only. Once it sees an A, move to the next state Q1. We have shown the transition of both the symbols A and B for Q0. Similarly, for Q1, if Q1 sees an A, move to the next state Q2 and accept it. But what happens if Q1 sees a B? So take this B. If Q1 sees a B, move to Q0. Similarly, suppose if Q2, on Q2 we have shown the transition for symbol A. What will happen if Q2 sees a B? If I take this B here, so the string will end with BA. We do not want that. What we want that string should always end with an A, end with double A. So when Q2 sees a B, take the transition towards Q0, and this is the diagram that will make sure that strings always end with double A. Hopefully this is clear to all of you. Now move to the next example. Strings have double A as a substring. Wherever we have strings having a double A as a substring, means once this criteria is fulfilled, after double A, once the machine has seen two A's, that is consecutive AA, it can have any number of A or B after this, and the string should be accepted. Now complete the diagram. What will happen if Q0 sees a B? Remember that strings can have double A as a substring. So if it has a B, keep looping here only. Any number of B, stay here. Once the machine sees a single A, move to Q1, and from Q1 again if the machine sees one A, move to the next state, that is Q2, and accept it. Now the thing is, what will happen if Q1 sees a B? If I loop here, this will result in string having BA as a substring. We might get some B in between. We will not put B here. So to make sure, to guarantee that we are having double A as a substring in this string, because the language requires that, we need to have that whenever Q1 sees a B, loop it back to Q0. So this is the diagram for deterministic finite automata for the language where strings having double A as a substring. At least one double A as a substring, because after that, once double A is seen by the machine, it might have more double A's with this loop A, B whole clean closure, because the loop, if I make a state like this is nothing else but A plus B whole clean closure, means any number of A or B, any combination of A and B could be included by this expression.